So thank you everybody for attending today. Today's learning opportunity is going to be centered on infection control and the reduction of risk through filtration and UV light. My name is Adam Santel, and I provide engineering support here at APA. I've been with APA for about 3 years now, and my job consists of working with engineers to find solutions to the problems they face in HVAC design every day. Questions for today's presentation will be proctored, so please use the chat function to submit any questions that you have. We will email the questions and answers in our follow-up email after the presentation. Our speaker today is Duke Weiser. Forward Cloud Duke Weiser III founded Environmental Dynamics Group in 1993 with several of his partners. Dynamic designs and manufactures systems for cleaning air and saving energy in a broad spectrum of applications. Just a few of their installed applications include government and military facilities, the world's most valuable art collection at the Barnes Foundation, and many laboratory and medical applications. In the current crisis, Dynamics systems are being installed in field hospitals. Dynamics headquarters are in Rocky Hill, New Jersey. Primary manufacturing is outside of Ottawa, Canada, and there are several satellite engineering and sales facilities throughout the country. Dynamic air quality solutions are sold around the world, and Mr. Weiser is an ASHRAE member. He has testified before OSHA on indoor air quality in the workplace and holds several dozen patents in the field of HVAC. Duke has spoken at Greenbuild, Green Buildings, New York, the International Conference for Enhanced Building Operations, the National Facilities Management and Technology Conference, and various ASHRAE meetings. For these reasons, we at APA are very excited to have Duke here today to present. And so for now, I would like to turn over the presentation to Duke. So Duke, when you like, you can go ahead and take it away.
I will share my screen and do this.
Perfect. Yep.
There we go. Let's go to a laser pointer for. Oh. So thanks for that introduction. That was great. Appreciate it. I didn't realize I'd done all those things. I'm going to talk today really about some of the issues related to infection control. Obviously, that's a hot topic in the news right now, and something that we're all concerned with. For example, thank you all for staying home and tuning in and not coming to a lunch and learn. Talk a little bit about that, and then what specifically how we can help, or the various categories of things that we can do in the HVAC industry. We've been designing systems for a long time to clean air in buildings, and so basically we do 3 types of projects. We do new construction, where the deliverable is less fan horsepower and MERV 13 or greater filtration for a new building. We do energy retrofits in existing buildings, and then also help with filtration upgrades in those. And then we also, another subset is helping customers with IAQ issues, diagnose and solve those. So we've always been providing clean air. It's just usually people have been asking us, recent years, what's my ROI? Now people are more interested in the air quality aspect. So a few of the, I'm sure you guys have all been following the news and reading the same journals, or many of the same journals that I have, so I won't spend too much time on this, but basically what makes COVID unique and dangerous is its interaction with people, right? People have no immunity to it. And that's really, it's what's novel about it. And what's dangerous about it. But in terms of the way it interacts with, the external world and things like filters and UV lights and disinfectants, it's pretty much run of the mill, right? It will die on a surface, it will be killed by UV light or disinfectant, it will be caught on a filter. But there's a variety of ways that it can spread, like any virus, right? Surface, I cough in my hand, I touch a doorknob, you touch the same doorknob, etc. So there's a lot of those various vectors of transmission, and infection control generally is belt and suspenders. It's about reduction of risk, not elimination of possibility. right? So in the HVAC world, we're primarily concerned with airborne transmission because that's what we're doing, right? We're moving the air around in the spaces. So like other viruses, SARS and H1N1, other flu viruses, the actual virus is quite small. It's an ultra-fine particle, right? It's smaller than 0.3 of a micron. But it doesn't usually travel that way. It usually travels as a part of a droplet nuclei, or they're seeing now it can also attach itself to particles in the outdoor air. So typically, the droplet nuclei are anywhere from 6 to 0.7 of a micron, all the way up beyond 10 microns, and that they are breathed out, sneezed out, coughed out from someone who contains the virus. The big droplet nuclei settle pretty quickly, right? And so they're falling to the floor, which is why the 6-foot distancing helps reduce that vector of transmission. The smaller ones, which the 1 to 3 micron ones, will stay suspended quite a bit longer. And the other fact is that as the droplet nuclei are exhaled, they're sort of in a bundle of moisture and other things. The moisture evaporates quickly, and so the bundle gets smaller quickly and is more likely to stay suspended and be entrained into an HVAC system. The virus by itself will be inactivated on a dry surface after some numbers of hours or days, depending upon the surface. But as I mentioned, they found a positive correlation between high particle levels and transmission rates, particularly particle levels in the outdoor air. And they've actually found the virus attached to these particles in the outdoor air. And the other factor there probably is people who live in high pollution areas already have sort of pre-stressed lungs. They're also finding that even if the particle settles, it will it can be resuspended into the air, either attached to particles and they're finding that when they were studying in Wuhan, coming up from floors and surfaces and clothing. So obviously again, infection control in this instance is a chain of activities and things that you have to do. Personal protection, washing hands, distancing, all of that stuff is all important. No one is more important than the other. But from our standpoint, how does HVAC and filtration play a role? So we're actually kind of fortunate because, in some ways, because after SARS and H1N1, there was quite a bit of research done on, what can be done to reduce risk of transmission in buildings. What are the HVAC measures that can be done? So we have quite a body of knowledge on how to upgrade and change systems. And this is directly from the ASHRAE position document. And in essence, what it's saying is that the transmission of SARS through the air is sufficiently likely that airborne transmission to the virus should be controlled, and that you can do that by changing building operating parameters such as filtration upgrades, outdoor air levels, airflow patterns, etc. And so the HVAC can play a significant role in preventing that airborne exposure in a building, and that's not surprising, right? Because when you think of critical environments, clean rooms, labs, hospitals, infectious disease areas, that's HVAC and filtration, right? So it's not surprising that we can apply some of those same techniques to other spaces. So this just sort of reiterates, this is also from the ASHRAE document, just sort of, again, underscores what I was talking about before. Obviously, the big stuff that gets coughed out settles quickly, but the smaller particulate will stay in the air for hours, right? And so if I've got, and what's my typical air change rate in a building? It's, 7 to 12 air changes per hour, right? So that means these things are definitely going to get, or are likely to get sucked up into the HVAC system if they're staying in the air, 1 to 12 hours. So What we don't want, what you don't want is your HVAC system to be the means of distribution of the virus throughout the space. So what does ASHRAE recommend to help stop that? Specifically, MERV 13 or better filtration in central systems. Now it's interesting, just as a factoid there, again, back in 2012 after SARS, they did a lot of look at, work around reduction of risk with various filtration levels, and far and away the biggest bang for the buck was going to 13 from anything below it. Going beyond 13, the benefits are increasingly smaller, but there's a huge bang to get to at least there. Using germicidal UV can also be an effective control strategy. Again, it's sort of belt and suspenders and reduction of risk. And so UVC in the 254 nanometer range will inactivate or kill viruses, bacteria, and molds. There's no question that's what it does. The question is, what is the intensity required to do that for a given organism? And do I have that intensity in the way I am applying the UV? The good news is with viruses, flu viruses, it doesn't take that much UVC to inactivate them. They're down at the sort of the lower range of 3,000 to 4,000 microwatts. Spore-forming bacteria and molds take quite a bit higher dosage. Maybe several dozen times that level. So also, in addition to that, localized supplemental air cleaning systems that may or may not include UVC to boost the air changes, in a patient area, so that I'm having a higher circulation rate of air there. Another big one is to increase, to the extent possible, outdoor air levels and ventilation rates, under the assumption, right, that outdoor air is essentially 100% effective at removing the virus. There's only so much you can do with, in an existing building, but when you think about it, the HVAC in most buildings is designed for thermal comfort versus contaminant control, right? And so the air comes in and gets mixed all up, as opposed to sort of a directional airflow that you would have in a clean room or operating theater, where you just want a continuous flow of air in one direction and not trying to mix everything all up. Obviously, room pressurization is a critical part of controlling the flow of contaminants within a space or building. And then the other one, interestingly, is the humidity. Humidity plays a role on both sides. It plays a role in people. If the humidity levels are too low, that affects the functioning of the lungs and nasal membranes in dealing with things that are breathed in. Also, as I mentioned before, the droplet nuclei start to get smaller quickly as they leave the 100% humidity, 100-degree air in your lungs, and you come out into the ambient air. So the lower the humidity level, more quickly they will get smaller. So looking at filtration, passive filtration, which is what's in most systems, are rated here in North America with ASHRAE 52.2, gives you a MERV rating. A passive filter, slight oversimplification, but it's basically a sieve. It's a mechanical filter, as they call it. So you're trading efficiency for pressure drop and energy. And actually, most of the cost of filtration is in fact energy, right? It's not the cost of the thing, it's the cost of the energy the fan go to push the air through the thing. The passive filter will tend to load on the upstream side. It'll tend to increase in efficiency as it loads. So this is the MERV test, and this is the MERV chart of what a MERV 13 filter means. And so it looks at three size ranges. It looks at the E1, which is 0.3 to 1 micron. It looks at the E2, 1 to 3 micron. And it looks at the E3, 3 to 10 micron. It doesn't look, it should be noted, it doesn't really look at anything below 0.3. Most filtration measuring standards don't, even though, especially in an urban environment, stuff smaller than 0.3 is most of what's in the air. And of course, that's where the individual virus lives, although, again, the virus rarely travels by itself. So a MERV-13 filter, what does that buy you? That buys you an efficiency in the lower range greater than 50%, but less than 75%. In the 1 to 3 micron range, it gives you an 85% removal or better, but less than 90. And in the E3, it gives you a 90. So it does, again, it's interestingly, but in the research done, this is your biggest bang for your buck in terms of the going from 8 to 13. So with a passive filter, the V8, which we'll talk about, one of our products. This is its operating range: the E1 of 94, E2 of 99, and E3 of 100. So a little bit better. So what is it that we have that can be some tools that might be able to help out in all this? We have a range of systems. I mean, we have things geared towards particle filtration, gas phase, UV systems. We have a range of systems that we use for various applications. So in this particular instance, probably our lead product would be the V8, which is a modular polarized media air cleaning system that would install in the filtration section of an air handler. In a standard MERV test, we have MERV 13, 14 versions. In actual operation, it's due to the various mechanisms, more like 15. Typically, we see a 92 to 99% reduction of ultrafine particles versus outdoor air levels in a building. And again, some of the mechanisms that I'll get to help us have an enhanced ability to do that versus a passive filter. By taking out those ultrafine particles, we're also taking out the gas phase contaminants and odors that are absorbed on them. So we're putting a pretty nice dent into the odors and gas phase. Again, we make carbon systems for museums and people that need carbon. Most people don't, but it's nice to have a little bit of gas phase removal. This system has the highest dust holding capacity on the market by an order of magnitude, and that means a lot less maintenance and a lot less energy. Normally, that's a oh, that's nice kind of a thing, but we're hearing from a lot of customers, they don't want to change filters. They don't want people in their building changing filters. They don't want to have their people change filters, and et cetera, et cetera. So if you have a typical maintenance cycle that's 3 to 5 years, at ASHRAE they went 7 years without changing their media. So it's a long maintenance cycle, which again means less risk, less exposure, less people. Another important element of it is it is an engineered system that is built to the specifics of a given air handler cross section, and so there's zero bypass around the filters, which is a critical part for any filtration, right? If I've got HEPA filters and I have a gap this big between them, I don't have HEPA filters, and so filter seal is critical. So that's our, again, that product is used in hospitals, labs, pharmaceuticals, green buildings, museums right now, and that would be your first line of defense would be something that will capture basically all the particles in the size range of concern for this specific, for the pandemic. So you want something that's going to catch all that stuff. In addition, if you want to start adding layers of protection, we have another range of products that use the same underlying technology, which I'll get to in a bit, but we couple that. In this instance, we use a different media. We use a relatively sparse glass fiber media, and we couple that with high output UVC. And so, most UV you see in systems is optimized for keeping the coil and the drain pans clean, right? It's downstream of the coil, above the drain pan, and that's great for what it does, what it's meant to do. Not really optimized for infection control. You do see systems with a whole big array of lights that are really optimized for a single pass kill, and that is something that can be engineered for sure. What we're doing is a little bit different, is we're coupling the high output UVC again with air cleaners with a translucent media, so we're able to capture and kill the pathogens on the surface of the media, and do it in tests using bacteria that is harder to kill than flu virus. There's a 90% kill after about 5 minutes, and so this system now is used often as a pre-filter for V8s in hospitals and other critical applications. This was, sort of fun fact, this was used as part of the anthrax cleanup. Not to kill the anthrax, they used chlorine dioxide in the buildings. They sealed the buildings up and they pumped them full of chlorine dioxide for a month. But when they flushed the buildings out, they didn't want anything live to come in, and so they used this system for that. In a research system, this does very good in terms of particle reduction and particle removal. Not as good as the V8, but it's up there with high efficiency MERV filters. And then lastly, in terms of the panel air cleaners, we have 1 and 2 inch panels that could go into smaller equipment that really have no capacity or space for additional high efficiency filtration. The other nice thing again is these could be coupled with UVC. We sell a lot of this product in smaller equipment, residential apartments, even fan coils and hotels, etc. But it has the same underlying principles and some of the same abilities in terms of an enhanced ability to take out the ultrafines and other particulate. So what is it that we're doing here? I got to switch back over to Arrow. So all of our systems rely our particle removal systems are based on the same sort of core technology, and we're combining elements of passive filtration with electrostatic attraction and a non-ionizing electrostatic field that polarizes the fibers and the contaminants in the air so they stick to each other more readily. So the basic building block is 2 external grounded screens, and then there's a center screen that is at a voltage and a shape, even though it's a high voltage, it's below the breakdown voltage of the material. So we're not creating any ionization or ozone, but we are creating an electrostatic field that polarizes the fibers on those media pads. As particles come in, the same thing happens to those. So they don't get a net charge, but they get a negative side and a positive side, and they stick to the polarized media. So a passive filter works basically through collision of particles with fibers. So even though I said it was like a sieve, it's really more like a forest in a way. It's where you're trying to things are trying to move through the forest, but they are hit, they are impact on the fibers. But a passive filter, loads essentially on 90 degrees on the 180 degrees on the upstream side. So we're taking those mechanisms of collision and capture, but we're adding a twist in that by polarizing the surface charge of the fibers, we're making them more attractive all the way around, and they're captured on all sides of the media. And one of the key factors of that is the ability to increase the collision rate of the particles, not only with the fibers, but also with each other. And so the particles form bigger chunks that are more easily taken out. and they also load all the way around the fibers. So that gives it a much greater dust holding capacity. And so it also, this is what gives us our ability to get down into the submicron sort of ultrafine range of particle capture. This is a, what does that mean? What does that do for us? This is a graph of dust holding versus pressure drop. And so switching back to my laser pointer. So this is dust held going to 1.4 inches, which is the, quote unquote, final static in the ASHRAE 52 test. And so these are various passive filters, and as you can see, it takes a few dozen or a few hundred grams to go from, everybody sort of starts in the same given range, and then it doesn't take that long to get up to the final static. And again, typically these guys are pre-filtered as well. So the V8 is this guy, and so we're holding a few thousand grams of dust, and that's because, as you saw, it's loading all the way around those fibers through the entire depth of the media pads. So the media pads themselves are an inch deep and 9 layers of different materials, versus a typical high efficiency passive filter is a relatively thin, relatively flat media that's been pleated up, and so it doesn't have a lot of loading capacity. It has a lot of surface area, but not a lot of loading capacity. So we're able to load through that entire depth. So what does that mean? That means that on new construction, instead of designing for this static pressure plus a pre-filter, which gives me a midlife of somewhere up in here, I can design around the V8 and have which I can change. Sure, I can change it here, but more likely I'm going to change it at twice the clean static or so, and I still then have a midlife of around 1/2 inch. So that allows me to lower my fan horsepower and fan selections from the get-go. On existing buildings, it can allow me to upgrade my filtration with systems that really don't have the fan static and horsepower to otherwise accommodate high efficiency passive filters. And these are the 1 and 2 inch or 1 and 2 inch V-banks. This is a graph of looking at, in a research system, particle levels at 0.3 microns. So the particle count at 0.3 micron in a research system. And what do you get there? And so again, what you see typically is that it'll go to a certain plateau, and the highest plateau is a MERV 13 filter, then a MERV 14 filter is the screen guy. The 1 and 2 inch V-banks of our glass media come in about the same place. So, and by far and away the V8, these guys are leaving 4 times more stuff behind than a V8 at 0.3 microns. And so it goes more quickly and further down than those other alternatives. So just recapping on that, so you're with the V8, you're getting MERV 13 to better than 15 performance. Typically a third the operating cost of a passive filter array. Reduced maintenance again, which a lot of people are interested in right now. Nobody wants to go change those filters. I mean, the sickest I've ever gotten was changing filters, not in recent weeks, years ago. So I always gown up. But because whatever is in the building is on the filters. Whatever is in your. And so we have the removal also of ultrafine particles, which again are a big deal in urban environments. That's mostly where you see those. significant reduction in VOCs and odors because of that. Typically, we don't use pre-filters, and less again sometimes on medical lab applications we've been coupled with UV. And again, a design midlife of generally around a ½ inch. In terms of cost of ownership, less cost of ownership, good ROI. A few, for instances, this is ASHRAE headquarters. The V8 is installed throughout ASHRAE headquarters. They, as I said, didn't change their media for a really long time. And they also have air acuity there. And so in monitoring the air there, they, the indoor air is always a lot nicer than the outdoor air. Current ASHRAE headquarters is sort of near the Beltway in Atlanta, so it doesn't have great outdoor air, but not atypical of an urban environment. This is 2121K, an office building in downtown DC. Again, a high level of ultrafine particles in the outdoor air, which you see in urban environments because of vehicle exhaust, kitchen exhaust. Basically, ultrafines come from combustion byproducts. Again, that's also the range where the virus lives, but typically, I'm more concerned about all the levels in the outdoor air. Inside the building, the levels were 92 to 99% lower than they were outside. And interestingly, the highest levels at that place were not at ground level, but up on the roof. The highest levels of ultrafines, because those particles will stay suspended indefinitely. This is at a hospital side by side, identical air handlers where they put us in Spain and did monitoring, and with clean media at peak loads, we had a significant reduction in energy. That would only become more pronounced over time with the enhanced loading that the V8 has. So those are some of the things we can do in terms of the, I'd be interested to get some of your input. I mean, I'm talking to people looking at things. I don't know. I can think of some places that we're going to need to go in our industry. I think wider application of MERV 13. It'll be interesting to see if LEED and WELL go back to MERV 13s throughout. I mean, remember the early versions of LEED required MERV 13 filtration throughout the building, and now it's just required on systems that see outdoor air. Obviously, if you're trying to control a airborne pathogen, you'd probably want to change that back to 13 inside too. I'm going to assume that people are going to want systems that are a little bit more optimized for contaminant control, which would include, again, directional airflow patterns that would take contaminants either up out of the breathing zone or down out of the breathing zone, but wouldn't sort of mix them up in the space the way most of our sort of ceiling supply return kind of scenarios do. I think people are going to want higher ventilation rates, or at least high ventilation rates, and not try and reduce outdoor air levels, which makes sense. But again, that's going to it's also going to require then greater vigilance on what is that outdoor air, how clean is that outdoor air, are you in a non-attainment zone? Do you need to add other levels of filtration or capture to that? Interestingly, one of the big vectors, and this didn't come out of this isn't new news, but maybe this none of this is new news really. It's just that people are more fired up to do something about it now. But one of the big vectors for release of pathogens in space is toilets, flushing toilets. And if you think of the way most bathroom exhaust is, it is pulling it up into the breathing zone, which is again sort of the opposite of what you want to do if you're trying to control it. So obviously, pressurization of the building, but also the individual spaces is critical towards impacting and controlling the flow of contaminants within a building. Right, I need to know where the air in my room is going, and am I pulling in air from other spaces, and how is that all flowing? I think that, whether it's UVGI, the upper room UVGI or other localized systems, I think that people may have an increased use or desire to have those kind of visible systems in a space, if for no other reason. Again, the sort of psychological reason. It's like, oh, look, there's my air cleaner, I feel better. Same with sort of supply, putting filtration in supply grills rather than, well, in addition to what's in the air handler. Because when you think about critical environments, clean rooms, etc., operating theaters, the biggest hammer is right before the air goes into space. It's not, 60 feet away at the air handler. You've got filtration there too, but your high efficiency filtration is right as the air goes, right before people are going to breathe it or have to go over their operation. And again, I think people, well, I know, because I know what we're being asked to do, but I think there will be expanded use of UVGI, and again, not just on coils, but again, more optimized for infection control, whether that's units, the upper room UV, which you've seen, that's been around for a while, to sort of capture stuff in a space, or whether it's a more aggressive grid in an air handler. But I think that's going to be, again, something that people are going to be looking to have. And when you think about it, really, that is I think this is going to continue the evolution of what has been happening anyway. When you think of the evolution of indoor air, I mean, for centuries it was just not freezing to death in the winter, right? It was a fire in a cave, and then people wanted cool air, and then people wanted the air to be, thermally between whatever 68 and 72, and not too hot and not too humid. But now people expect the air to be clean, right? And that's been an increasing expectation. Let's get smoking out of buildings. Let's look at our outdoor air. Let's increase our filtration levels. All of that stuff. I think this is only going to be another big step in towards people really being sensitized and having a desire and requirement for systems that not only deliver air that is the right temperature, but air that has no bad stuff in it. So anyway, that is. Thank you very much. That is all I've got. But I'm happy to take any questions, comments, etc.
Duke, there's a bunch in the chat meeting that maybe you should switch over to and take a look at it, maybe read out to everybody. And maybe that's a nice way to keep them in order too. If anybody has questions, we will record this, and all the answers will be followed up in the recording also for everybody.
So if I stop sharing, where will I see that? Where will I see the chat stuff? Sorry, being a WebEx dummy.
When you put your cursor on, you'll see a little blue circle that says like chat.
Yep.
You should see it pop up on the right.
Can the organizers turn off the beep notification? I think they did that. Reference for MERV chart. What is the reference for the MERV chart? Just the ASHRAE 52. That's just taken right out of this ASHRAE 52 too. Are there special requirements? I mean, there are special requirements. So, sorry, the question, maybe I just reading it out. Are there special requirements for changing filter system, and is this done by typical facility group or contractor vendor? I'm not sure in that instance if you're referring to, is there in terms of changing the media out of an existing system or installing our system, but I'll try and answer both. Obviously, people should always wear PPE to change filters, period. I mean, whether COVID or not. But in this specific instance, obviously the ante has been raised, and the filter change out procedures will be even more important. Most systems aren't bag in, bag out the way a HEPA system would be in a supercritical environment. So this has to be done carefully and mindfully by people who are properly trained. In terms of putting our stuff in, I mean, typically what we do is we take out, there's various versions of it, but typically we will take out what is there and put in what we have. That's usually the most efficient way. Okay, sorry. Average cost increase, pushing the MERV 8 to MERV 13 filters. Some of that really depends on the system and what do you have. I'll let Andrew and because he'll know better, what that entails in your market, right? So it really depends upon the install, because usually a MERV 8 filter is a 2-inch slide in, and much of the time it's going to be a 2-inch flat slide in, and so usually there's going to be some reconfiguration of the filtration section involved to switch it up. Because even with passive filtration, I can't, if I've got a system that was designed around flat MERV 8s at 500 feet per minute, I'm going to have trouble sticking in a flat 2-inch MERV 13 at 500 feet per minute. And I'm also going to change the MERV 13 a lot. Anyone considers? Okay, sorry. What is the recommended wavelength? Well, typically for UV, some of these have been UVC. You want 254 nanometer, right? That's the optimum germicidal UV. You do see, also in the C band, and that's something to be mindful of and to sometimes watch out for. 185 nanometer will make ozone, which some people use. I mean, ozone's fine in an exhaust system or in specialized uses, but you wouldn't want to use it in a building where people are breathing. So, typical germicidal UVC lamps are 254 nanometer. We'll follow up with email. Are there studies show the reduction of transmission of COVID? Yes, there are. Are there studies or information that show the reduction in transmission of COVID-19 viruses versus recommendations on higher outdoor air filtration or implementation of UVC? There's no studies at this point on COVID-19, right? I mean, so the studies that would have been done to date would have been based around SARS, which again, similar size, similar thing in terms of what it is and how it interacts, different in how people deal with it, or its effect on people. So there are those studies exist, and I'll give them. They're all publicly available. I mean, Bill Banfleth has done a lot. The NAFA did a whole big thing on reduction of risk with various levels of filtration as well as ventilation. So yeah, that stuff all exists, and I'm happy. I'll share that with Andrew, and he can pass that along. Are there small? Yeah. So for fan, again, I think I may have covered that. We do have some stuff that can go onto a fan coil because again, you're usually limited there. You're usually really limited in terms of static pressure. And then often limited in space. But we have systems that can go on fan coils or even VRFs. Definitely VRFs are the easiest, but yes, we can do all those things. Thoughts on how UVC's effectiveness changes as a function of time of exposure, airflow, and intensity. So UV, anybody's UV, right? So UV dosage is microwatts per centimeter squared per second, right? So energy over a given area over time. And, or some people measure it in joules, which is basically the same thing, kilojoules. a given organism requires a given dosage of UV to become inactivated. Now, the good news is that if it takes, as an example, 10,000 microwatts to kill something, I can hit it 2 times with 5,000 or 10 times with 1,000, and I'll still have that same impact. So I don't have to do it all at once. I can do it, and I also can impair it without actually all the way inactivating it. So, but yes, the trick is I've got an airstream that's moving 500 feet per minute or 1,000 feet per minute down a duct. I don't have a lot of time, so how do I ensure that I have enough intensity to inactivate? I mean, in some ways, it's just math, right? You're just trying to figure out, okay, how fast are they going? What's the, if I'm optimizing it for a specific organism, what's the dosage required, and how do I ensure that dosage, and with a factor of safety, and a lot of, and there's all of that's been done. There's Penn State has done a ton of work on that, as has AHRI. So I'll share those with, that all exists. So, but it is a challenge, right? I can't just stick, so I can't just stick a single lamp in a duct and call it good, right? I have to have enough intensity. And lamp output does degrade over time. And so typically your maintenance schedule for lamps is every 18 months to 2 years anyhow. And it also can be affected by temperature, which is but within a range. I mean, so you can design systems that are made for cold, all that. But again, what we try to do is capture it on a translucent surface and then hit it. So our time variable goes towards infinity. And so, so that's our theory of operation. So it's a little, and we've done a lot of work and research on that, typically in conjunction with food processing, because that's usually when people care about airborne stuff. They always should care about it, but usually it takes something like this to make them. Is UVC certified or third party? Is UVC's ability to kill pathogens, kill efficiency, or other metric certified by a government agency or other third party? Yes. I mean, I don't know if it's certified. It's well-trod ground. This isn't new stuff. People know. You can go to. There's a whole long laundry list of pathogens, and exactly how many microwatts it takes to inactivate them. That all exists. I mean, that's not. I mean, this isn't proprietary stuff, right? Using UV to kill stuff. That's what the sun does every day, right? And so, and literally at this point there are, and that's one of the things that this whole pandemic has pointed out, is the supply chain, right? And our stressed supply chain. So there's literally like 3 companies in the world that make UVC lamps for HVAC. And there's a lot of people that sell them, but there's 3 people that make them. There's not a lot of slack in the system, but again, if the ability of UVC to kill stuff, that's not a no question. Ultrafines are typically defined. This question is, how are ultrafine particles defined? Ultrafines are usually defined as stuff that is less than a 0.15 or less than a tenth of a micron. And again, so the MERV chart starts at 0.3, as does the HEPA test, is all 0.3 micron test. It's sort of a standard thing, and that's not. Part of that is because that's generally a pretty high penetration rate. The particles in the 0.2 to 0.3 micron range are big enough to have some momentum, but are small enough to be hard to catch. The really little stuff in the air kind of moves a little bit randomly, and can be, which increases its collision rate. By putting it in a field, you make that happen even more quickly. But that's what. So, that's what I'm saying. So MERV 13, 14, even with no power. Someone asked, sorry, what is your MERV rating without power? And so in a MERV test, one of the vagaries or quirks of the MERV test, it's currently the only test a worldwide test that still uses carbon in the test dust, which is a historical vestige that made for quick filter tests, but is not something that is present in normal dust. So it shorts out anything electronic. So you're only as good as your turned off rating in a MERV test. And that's why we say in a MERV test without carbon, which is how you are in a real building, we're MERV 15, 16. Is there a proven UV air purifier that you recommend? I mean, again, it's all UV is UV, and so the question is, what's the intensity of the lamp, and is it applied in a way that gives it enough contact time and intensity with what you're trying to inactivate? And so I think it's really just I don't have one specifically. I mean, there's a lot of high output UVC lamps out there, and it's just a matter of, are they used in a way that will allow them to work, right? Handheld lamps for decontamination possible due to lower power required. Well, again, that would, question, handheld lamps for decontamination possible due to lower power requirement versus typical AHU mounted systems are still dangerous to human tissue. So yeah, UVC, high output UVC is quite damaging to human tissues, especially your eyes and skin. I can speak from experience on both of those. But I don't know if you've ever burned your eyes welding, but it's kind of like that. But anyway, so you can't really use UV in a space where you're doing that. A handheld system would allow you to inactivate surfaces, right? I'm assuming that you would take it around. And there are hospital geared systems that are having this giant array of UV lamps, and you're supposed to wheel it into an unoccupied room and blast the room. So that would certainly kill things on surfaces. It wouldn't do much, again, for the airborne stuff. And so, but there's different. But I don't think that would be. I don't think that's an either or. I don't think some sort of a handheld or stationary system that is killing things on a surface in a room, in an unoccupied room, is instead of putting them in the HVAC system. Again, it's sort of belts and suspenders and the stuff. And so you're trying to do everything you can. You don't just do one thing. Can we use your system if you have humidification inside an AHU? I would put it upstream of humidification. Typically, it depends. I mean, the air cleaners are fine, as long as it's not condensing moisture. And again, that doesn't make them blow up or hurt them. It makes them a MERV 13 or 14. But again, you don't want to put filters, anybody's filters, in a place where they're chronically going to get wet. And so I don't know enough about I've seen humidification systems that are properly designed and don't have that impact, period. And so I think you'd want to look at that. But if it's something where the walls of the air handler are getting wet, then you might want to put it upstream.
Nicely answered.
And does ASHRAE have a UVC application guide? Does ASHRAE have a UVC application guideline to ensure optimal application of the product? AHRI has and I'll share that with Andrew, has a big fat paper. There's a couple of big studies out of Penn State. Last, what do you say about bipolar ionization by either electrode or lamp generated in the supply duct? Ionization makes particles stickier, right? That's what it does. They're sort of, and so in when you're ionizing the air, you're putting ions into the air, and those ions will attach themselves onto the particles. Typically, historically, ionization was the pre-charging section of an electrostatic precipitator, and downstream of your ionizing section, you had oppositely charged plates because opposites attract. Charged particles want to stick to oppositely charged surfaces and grounded surfaces. So it can certainly play, ionization of particles can certainly play a role in control of how those particles behave. In this specific instance, I think it could be a bad thing. I know from, we do a lot of grow facility work with our carbon systems in particular, but with both. I know, for example, that the problem with charging a mold spore or a droplet nuclei is it then wants to stick to a grounded surface. And that's people, surfaces, ductwork, whatever. So I know specifically that, you know, an ionizing company is being sued by a grow facility because the mold spores were ionized and stuck to the plants and ruined the entire crop. So I don't have any, you know, specific data as it relates to viruses in the air, but I would think that that same phenomenon would be a possibility if I'm ionizing, you know, airborne pathogens. So they're going to want to stick to something that's grounded, and people fall into that category. You would maybe want to do that, but you know, if you wanted to do that, you definitely want to do it upstream of something that could capture it. Let's put it that way. And I think, is that it?
Yep, I think there were just, can you hear me, Duke? Yep, so I think just one person asked who our competition is and how they compare to Dynamic.
They're much worse. Well, again, I mean, our competition is there's more than one way to skin a cat, right? I mean, you can use high efficiency passive filters. You can use different UV systems. There's a lot of ways to do it. We think the way that we do it offers a lot of advantages, but it's, you know, there's more than one way to take stuff out of the air. And so I guess that's our biggest competition is frankly people doing what they've always done, and not something new. But we've been doing this for a while, so we're getting.
Duke, one last question, if you wouldn't mind, unless anybody else, some on the chat. Could you respond back to some other things, such as the environment, waste, considering changing filters out annually versus dynamics, and then the energy consumption? Hitting those topics. We didn't really hit them hard.
Didn't hit them too hard. No, sure. So yeah, obviously, you know, if you're changing out filters every 3 to 5 years, there's a whole chain of things that you don't have to do now, right? You don't have to order them, you don't have to store them, you don't have to dispose of them, you don't have to, you know, bring them up and down in your dirty filters up and down in your building. I mean, I don't know about Boston, but you never know what's going to resonate with people. But in New York, for example, New York City, you're not allowed to keep filters in your mechanical room, so you can't have your next change out of filters in your mechanical room. It's against the law. And so, you know, so that means you have to put it in some other space or not have it or bring it in. And, you know, so they're like, I don't, you know, so that's a big deal. And so, but again, and especially now too, so there's a normal savings associated with that, both labor and time and disposal and all that good stuff, and sustainability and space and a dumpster and blah, blah, blah. But now, of course, nobody wants to change filters and go through the increased level of what you would have to do that. And in terms of the energy, you know, again, yes, we do, you know, typically the reason a big part of our business is energy retrofits into existing buildings. Because, you know, versus a high efficiency passive filter array, you know, we will save 2/3 typically the operational and energy costs, and that's due to that loading and the fact that, you know, you're not really ever going over 7/10 of an inch of static. So so we have a pretty significant payback based on just that. So does that cover it?
Yeah, I think that's everything. If anyone has any other questions, feel free to put them into the chat there too.
Finishing up on that, just to put some numbers around it, but and I think we did that was a slide of but you know, in a 30,000 CFM air handler with MER 14s and pre-filters, you know, we would save about 90,000 kilowatt hours a year. So that's sort of puts it into put some numbers around it. So that was great. Thank you.
Yeah, so a few things to mention to everyone before closing. You will receive a follow-up email with a link to a recording of this webinar. Answers to the chat questions and a few bonus materials from APA will be in there too. It'll be sent to the email that you used to register for the webinar. Please stay tuned for more upcoming webinars that we'll be putting out soon. And if you have any ideas for a webinar topic that you would like to know more about or would like us to present on, just let us know, as our goal with these webinars is to help answer questions and find solutions to the problems you face every day. So from everyone here at APA and Dynamic, we hope you have a great day. Stay healthy and stay safe.